All right, it's Wednesday afternoon, which means, you guessed it, time for another Grass GIS practicum. So get your grass started up till you see the, now familiar grass startup window. We're going to be working with the same Wadi Hassa WGS 84 UTM Zone 36 North location that we used the last couple of times for Project 2. Only now we are actually going to be starting Project 3, in which we are going to be doing a predictive model. In particular today we're going to be working with the map calculator. So what we want to do very first thing is to make a new map set. Alright, so remember, we're trying to be organized with our GIS data. We're going to do all of our analyses for Project 3 in a separate map set just to keep them all separate from what we did in Project 2. So we'll call it Project 3, right? Makes a lot of sense. So we do that. So now we have permanent Project 2 and Project 3. Okay? Once you've got this and Project 3 is selected, just start up grass. So the first thing that we're going to want to do, once grass is loaded up here, is to make it so that we can still see the maps in our Project 2 map set. By default, it's going to hide them from us. And the way we do that, the way we enable that, is to go up here to the Settings menu, and then go down to where it says Grass Working Environment, and the very first one says Map Set Access, g.mapsets. And it's important that this is map sets plural and not g.mapset, which is another one over here that lets you change the current map set you're working in. So we'll pick the first one, Map Set Access. And it gives us a little list here of all the map sets in this current grass location. Those that have a checkbox next to them, we can see the files in them, and those that don't, we can't. Okay? So by default, when you make a new map set, it's only going to show you permanent and the current map set. And all the other map sets will be unchecked. So you just need to put the checkbox, just check the checkbox next to all the map sets that contain maps you want to actually be able to see from within this current map set. Okay? So we've done that, we'll click OK. And what we're going to do today, we're going to focus on using the mapcalc. We're going to learn about it generally, the map calculator. And then we're going to learn about how to do a real general version of a predictive model. If you're following along with Project 3, there are a few more sort of steps involved, or there's a more involved set of things that I want you to do for Project 3. But this is going to follow basically the same workflow for the map calculator, just in a slightly more simple format for today. Okay? So firstly, the map calculator. It's under the raster menu tools because, well, it's for raster map analysis. And it basically lives here by itself, a raster map calculator, or r.mapcalc. I will often just refer to this as the mapcalc or mapcalc, a mapcalc statement, or sometimes I'll even just say map calculator. All right, so these things are interchangeable terms, just so you have that in your mind. So go ahead and click on our mapcalc. And you'll get this little window here that looks, well, it really kind of looks like a calculator, which is great. It has some buttons over here with some funny symbols. We've got some pull downs with a bunch of other weird things in here, a few fields, some parentheses, and then a big area here that says expression. So we're going to take a tour of all of this here in a second, but first let me just talk a little bit about these funny symbols and some of these things in here. And I think it's probably a little easier to just sort of pull up the help page for our mapcalc, okay, which I just have preloaded in my web browser over here. Now it's worth spending some time with this help page. It's not terribly long, but there's a lot in here. And when I first started using Grass many years ago, actually a lot of the custom modules that you find in here, well, a lot of them didn't exist yet, or they weren't as robust. And so I found myself using the map calculator for almost everything, and I found it really, really powerful. And it still is one of the most powerful things that you can do in a GIS. And most GIS software will have some kind of map calculator. QGIS has one. I'm sure the Esri software, I know they have one. And Surfer and Idrizi and all those other things probably have one too. The Grass map calculator is really, really powerful. And there's a lot of things that you can do in it pretty intuitively once you wrap your mind around how it works and you get a good sense for the syntax of the little statements that you have to write. So The first little segment here, highlighted in gray, shows all of these little symbols and what they mean. And if you look through it, you can see a few things that are familiar: plus sign for addition, minus sign for subtraction, multiplication, division, that kind of stuff. And then a few other things that are really interesting: like greater than, equal to, less than, not equal to. We have ands and we have ors, we have modulus, and a few other things. We have nots. So what these things are, we call them operators, logical operators. Some of them are arithmetic operators. Some of them are what they call bitwise. Typically, most of these things that are called bitwise, I almost never use. We almost always use the arithmetic operators or the logical operators. The arithmetic ones are the ones that you probably already know: exponentiation, addition, subtraction, etc. These ones you probably also know, you've used before. This is equal to that. This is greater than that, right? And some of them are a little bit differently. You have ands and you have ors, right? But basically, between all of these, you can do basic algebra, and you can also do logical statements, if-thens and if-not, that kind of stuff. And between the combination of those two things, you can do a lot of manipulation of your data, right? If slope is greater than 10, multiply by 20, otherwise divide by 15, right? There's all kinds of things that you can think of, right? So these are really powerful, just these little symbols in and of themselves. But also, if we kind of scroll down here a little bit, we come to another big block of gray, and we have functions. And the functions add an additional level of complexity, right? So we can do bigger if statements in which we can have our logical operators. This is how we do if greater than whatever, right? We can do logarithms. We can do cosine. We can do tangents. We can change integer values to floating point values, right? We can round things up. We can pick random numbers. We can take square roots. There's all kinds of very, very powerful things we can do. In fact, we can just make a moving window that goes across a map, specify a window of a certain number of rows and columns. We can say, do something to the cell to the right of the current cell. We can do all kinds of really, really powerful things, right? Today, mainly what we'll end up talking about mostly is the set of if operators over here. The rest of these things are really powerful, worth exploring as well. But I think probably the if statement combined with our logical operators and our arithmetic operators up above, even just that opens up almost endless number of possibilities for manipulations of your raster map data. So it's not a very big file. I recommend you sort of looking over, and especially looking at those two little gray sections that we talked about, the functions and the operators over here. Okay? And just as a little bit of a preview, what you can do is chain a lot of these things. You can make these really extensive map calculator statements. This is one right here. This is from a bit of Python software that I wrote, an add-on for Grass. It's maybe 1,200 lines or so of computer code. But many of these operations are actually map calculator statements, and a lot of them are conditional statements, right? If so-and-so is less than this, then do this crazy mathematical thing over here. Otherwise, make it this other value. And then again and again. And of course, I've got these things chained one after the other. mapcalc, mapcalc, mapcalc. And then a bunch of other programming stuff. But a lot of the things in here are mapcalc statements to manipulate data and to create interesting combinations and different outputs that you can't do with the sort of standard Grass tools. All right? So it's a little preview of, let's say, extra advanced GIS that you might get into somewhere down the line. But let's take it down a notch and let's go back to our humble little map calculator over here and just do something really, really simple, okay? So now you see what these little buttons are. Now you see where the functions are. Over here in this field is the name for the new map that you're going to create, the new raster map. This here is a way to pick existing raster maps that you're going to base your analysis on. And then, of course, you very often want to use parentheses to sort of nest all of these functions. And I'll just say right now that you can indeed click on a button here and have it be entered in the expression field, but you can also just enter text with the keyboard. And I almost always just use the keyboard rather than pushing these buttons. It's nice to have them there to remind you what's what. And picking the functions is also pretty nice. So picking an if statement puts it in there and puts the cursor in the right spot, so that's pretty good. But I've been doing this for a long time, and I often simply just type things, okay? So let's start off with something really simple, okay? Let's pick an existing map. We'll go into Project 2, where we made a slope map, and we'll find our slope map over here. And really simply, I'll click the buttons for you, times 2, right? This is really simple stuff. So we'll just make the output, we'll name slope x2, right? Slope times 2, like that. We hit run, and there you go. And we have our slope map over here. And if we do our query, we'll get values that are twice what they should be, right? So in that case, it was 5, 49, 60, 50, etc. If I get into some of the really high slope things, we'll get really astronomically high values of slope over there because I multiplied them by 2. So you're like, okay, I think I get what happened. You took the value for each cell, and across the entire map, you just multiplied it by 2, right? That's exactly right. Remember, this is like a big spreadsheet where the colors represent numbers. And like in a spreadsheet, you can very simply do that kind of mathematical stuff. You multiply the map by 2. What you're doing is multiplying every single number in every single cell by 2. And your mind should be racing now, thinking, oh, if I can do that and it happened that quick, think of all the things I can do. What if I took 2 different maps and I multiplied them together, right? Well, what kind of crazy map would that make? So let's try that. So instead of multiplying by 2, let's multiply slope by, let's multiply it by aspect and see what happens over here. So we'll just hit, we'll change the name over here, slope x aspect, right? Slope times aspect. And then we hit run, and it goes pretty quickly. And, well, okay, it's sort of changed a little bit, and the slope and aspect are related, so, I mean, the patterns kind of look the same, but if I do my query again, I get very different values, 3,873, 4,400, whatever. It may not mean anything, because we just multiplied these 2 values together, but you're starting to realize that the value of slope in, let's just show this sort of slope map, the base slope map over here. Where are we? Slope right here, right? That looks like this. And the base map aspect, which will load up again right there, has these values. So these go from 0 to 360, and these go ostensibly from 0 to 90. You multiply whatever is in the aspect map at any particular cell by whatever's in the slope map at any particular cell, and you end up with this, a sort of weird combination of the 2. And you might be thinking, oh, if I can just multiply them, I can take an average. And everyone knows that the average is simply 2 things added together and then divided by the total number of things that you had to begin with. So slope and aspect right there. And here we have, I'll just put av slope asp, right? And I'll hit run. We will make a new map right here where we have something that's halfway between the slope and halfway between the aspect, right? So it's starting to make sense, I think, in your head as you do this and you're following along. And now you want to think, okay, why don't I do something a little bit more useful rather than these kind of random things? So first of all, what I'll say is that experiment with all of this stuff. Additionally, think what might be actually important, a measurement to actually be important. So there may be a reason to multiply slope times aspect or divide it or whatever, but maybe there's no reason to do that. Instead, you want to do something different, okay? But what we're going to do right now is change tracks just a little bit, and we're going to think about using these logical statements, these functions like the if function, and then some of these greater than are less than. So again, let's make a real simple statement, and let's do an if statement here. So I'll just pick a basic if statement like that. It's not showing up because it's already selected, so I'll just write it here like that, if statement like that. It has the parentheses, and you got to have the parentheses. So the if has to be outside the parentheses, and then you have to build your function within those parentheses. So the standard way that this works is you write if map, and then you have conditional, I'm just writing these words in there, value 1, otherwise value 2. And it looks like that, all right? If map and a conditional statement is true, it will do value 1, and if it's false, it'll do value 2. So the way this actually looks like, so let's just stick with slope. So I'll go down here, and I'll pick my same slope map that we were working with over here. So if the slope map is, let's use less than or equal to 10, we'll code it with 1. Otherwise, we will code it with 0, right? So you read that from left to right. If slope is less than or equal to 10, make the new map with value 1 in those areas. If that's not true, make the map will have value of 0, right? So in this case, I will call this low slope areas, right? Just to make it abundantly clear what this is. And now when we hit run, oh, interesting. We get a what we call a binary map, which only has values of 0 and 1. So anywhere that's value 1, which in this case should be the purple value, no, it should be the yellow values, that had slope that was 10 degrees or less. And anywhere in this case is purple, which has values of 0, had slope that was greater than that. And that's really cool because now we can start to parse up our landscape based on this logical condition, right? If the slope is flat, well, that's actually meaningful in many ways because people are attracted to low slope places. So we might be like, hey, you know, that's a really interesting thing. We could use that as one of the bases for a predictive model. So we have to come up with some sort of meaningful threshold there. And I just sort of made that up. Well, I didn't make it up. It's actually derived from theory. Lots of observations of farming land use say that people tend to put their farm fields on slopes of 10 or less, 10 degrees or less. So that's an expectation derived from theory to make that threshold. The other thing that I could have done is taken a subset of sites. I can very simply pick, let's say, the villages that I queried last time, right? And I could overlay those on top here. You can't really see them because they're all in there. Let me just, there we go. So those are all my villages, right? And I could overlay them on top of slope like this. And I could upload the values of slope into the table just like we did before by going to vector and update attributes, and then going down to sample raster maps at point locations, right? And I would then just pick slope over here, and I would upload them into the table for that particular thing, which I think I already did last time. So we have over here, well, okay, we have the streams and a few of the other things that we did before. And of course I could get averages. I could get the average slope or something with, let's see, where is it? I always have to look this stuff up. The v-univar, which is what I'm looking for. So let me actually just launch it from here, right? v.univar. Okay, so I can simply go to my villages, and I could pick the name of the column. This is all streams and stuff like that, and get the mean, which is, where is it? Right here. So the average for that particular place was 1072. If I did slope, it would give me a mean slope I could then use the mean slope as the cutoff. Or I could take the mean and I could look at, for the standard deviation over here, I could subtract the standard deviation from the mean to give me a sort of lower threshold that says most of my sites are at slope of this range or above. And I use that as the cutoff, okay? So whatever I find, whatever the value for the threshold that I would use, back here in the map calculator, that's what I would put in this segment here. In this case, I chose 10 degrees, but it could be something else, right? And we can do this for a variety of things. So I'll just delete this one, and I'll pick the walking costs or from the streams, which is in my project 2. So streams walking seconds, and that's exactly what I queried with my vUnivar, which is, did I delete it? Okay, hold on. Let me get my vUnivar back up over here. Okay, here we are, vUnivar, and I pick my villages, and I pick my column again for streams second, and I hit run again. And okay, so I'm going to use the mean, and where's the standard deviation right here. So I'm going to bring out my little calculator tool on the side over here. This is literally just the little calculator tool. So I'll grab my mean value here, and I'll copy it, paste it in here, right? And I will subtract my standard deviation. Okay, so mean minus standard deviation is 163. So actually, let's see. In this case, I wanted to add them together because I want to be inclusive. So mean standard deviation away from there. So let's see, 1982. That's going to be my cost cutoff, right? So I'm going to copy that. I'm going to head back to my map calculator over here. So I'm going to build my if statement. So if, parentheses open, streams walking is, in this case, less than or equal to my cutoff, I'm going to make it 1. Otherwise, we'll make it 0. Okay, so what this says here is if streams is less than or equal to this cutoff that I defined by adding 1 standard deviation to the mean. So if it's within this distance from the nearest stream, we're going to code that 1. Otherwise, we're going to code it 0. Okay? And this is going to be close to streams, right? That's just what I'm going to call it in this case. We'll hit run. And there we go, right? So the yellow areas are 1s and the purple areas are 0s. So now, let's take a look, all right? Let's bring this down here. And let's do this, okay? So we have our close to streams, these are the yellow here, and we have our flat areas, the yellow over here. Now, wouldn't it be nice to combine these two to suggest that if the area is close to a stream and in a flat area, then it's a likely place for a site. Now, that's already a pretty interesting predictive model. In project 2, I'm going to ask you to add 2 more variables to that, but for now I'm just going to demonstrate how we would build that very simple predictive model. So, you guessed it, back to the map calculator. And you might already be thinking, how would I do that? How would I do that? How would I combine those two things? Well, the easiest way to do this is by simply averaging the 2 maps together. So let's do that. Let's pick our close to streams, and we'll add it to our low slope areas. We'll put all of these things in parentheses. Remember, this is going back to when you took algebra. And then we'll divide it by 2. In this case, there's 2 maps, right? If there were 3 maps, we divide by 3. So you add the maps together and you divide by the number of total maps, and that's the average, right? And in this case, I'm going to call it predictive model streams and flat. I'm just doing this to be overly descriptive in my name. You don't want to make the name too long because that can cause problems. This is already probably the longest name that you would want to do. Very typically, I would do strflit like that just to make it a shorter name, right? Predictive model strflit flat streams, right? So let's hit run. And there we go. So now what we have is a model that says, okay, 1 and 0. Interesting. So basically, anywhere that we have 1 in this new model, we have some area that's close to a stream, but that's also flat. And anywhere we have a 0, we have something that is basically neither flat nor close to a stream. Or it's either close to a stream and not flat, or it's flat and not close to a stream. So we've made, basically by multiplying these things this way, we've actually taken two binary maps. These are integer values, right? So 1 and 0, no decimal points. Because they're an integer map plus an integer map with an integer value, we made the output was also an integer map, meaning we also got 1s and 0. But in reality, if we want to really take the average, we want to have values that fade between 0 and 1, meaning there are more likely places and less likely places. To do that, quite simply, all we have to do is make the 2 into a 2.0. And by doing that, dividing by this floating point value, we're going to get a very different output. So when we do this, we'll just check our box to overwrite output files. We'll hit run. And now you'll see the map looks very, very differently, right? So now when we query across it, we get some decimal values as well. We get 1s, we get 0.5, and we get 0 in this case, right, under here. So we have 3 things. So basically now what we have are anywhere that's 1 are both flat and close to a stream. Anywhere that's 0.5 is either flat and not close to a stream, or close to a stream and not flat. And anywhere that's 0 is neither close to a stream nor flat. So this is a little bit more nuanced, a more useful predictive model that says anywhere that's yellow, that's 1, is really likely to have a site. Anywhere that's this teal color, or 0.5, might have sites, a little less likely. And anywhere that's 0 is probably very unlikely to have a site. And of course, we've got our Wadi Hassa villages, which I'll just change their symbol here so that we can see them a little bit better, like that. So there they are, right there, all these little points. In fact, I'll change them. I'll make them red inside so you can see them really well. Okay, right there. And if we want to load up a second data set, I'm just going to load up the North Bank survey, which will show up out over here. We could use these as a validation set. So if we built our model based on querying these red sites, we want to withhold another set of data from the other survey, perhaps from the Wadi Hassa survey. Or if we use the Wadi Hassa survey villages, we would test against the Wadi Hassa North Bank survey villages as our validation data set. And we would see if we upload the value from our map that we just made, our predictive model, into the table for the Wadi Hassa North Bank survey villages, do we get all values of 1? Do we get some values that are 0.5? Do we get a lot of values that are 0? And what that would tell us is, did our predictive model do a good job predicting the location of the sites in the validation data set? So I am going to leave it for there for now. And we will continue to work with this data set moving forward. We will do interpolation which is next time for our next practicum, which we won't have to do for project 3, but which is a really useful thing. After that, we'll do cumulative viewshed analysis, which we'll include eventually in our predictive model for project 3. So I guess that is it. Until next time.